Good morning. My name is Vicente Geral, and I'm going to present the 3D printed modular stellarator USD2. First, a short background information. Later, the USD2 conceptual design, the engineering concept and design, the experimental validation by construction of USD2, and the future work. The work is developed in a framework of very low funds and human resources. Therefore, the relevance of the work is more the methods developed to build the device, more than the size of the device or the possible plasma experiments with the device. Up to now, only private funds have been obtained for the design and development. The work is research and development and innovation in engineering, focused in new construction methods for accelerators. We know that the geometrical complexity of accelerators is one of the main problems of this type of device. So, faster and lower-cost methods to deal with this type of devices, accelerators, I think may contribute to increase the potential of these accelerators and experimental machines, and also for future fusion reactors. Some essential data about USD2 so you will be able to understand better the presentation. USD2 is a modular accelerator of the type quasi-isodynamic. The major radius is only 260 millimeters and the plasma volume 10 liters. And it is being built currently in Spain by 3D printing. It's not only a concept, we are building the accelerator. The objectives: develop new beta construction methods for accelerators. And beta includes faster methods to build these devices, cheaper and simpler methods. Also, validate these construction methods by the construction of a small accelerator, and this accelerator is used to do. Also, generate demonstration effect. That is, perhaps some universities or research centers may be encouraged to build these accelerators or even other fusion machines by 3D printing and contribute to my PhD thesis. Here we see the conceptual design. These are modular coils, and these are planar coils, and large cores here. And this is the current state. Only one period has been manufactured by 3D printing. USD2 is not the first accelerator built by new innovative methods. Before, USD1 accelerator that is even more smaller, 366 millimeters, was designed, built, and operated from 2005 to 2007, also in a personal laboratory. The cost of the materials for the whole facility here were only 3,000 euros, because most of the materials are second-hand. And the coils, these modular coils, were built by an innovative milling machine, a machine that was working in toroidal coordinates, that is, in poloidal and toroidal coordinates. USD2 conceptual design. The aim was to use as much as possible the physical design that the researchers supplied. In particular, the QPS quasi-poloidal accelerators for which the quasi-isodynamic accelerators from IPP mass plant of 2 periods, 3 periods, and 6 periods, and also the NCSX improved for turbulent transport received from Princeton. They were studied, compared for confinement, for compactness, and other concepts. There is no time to talk about this. And at the end, I decided to take the configuration from the quasi-isodynamic accelerator of 3 periods. That is this. This is the last crosswalk surface and some initial coils. After having taken this decision, I wondered, would it be possible to modify this configuration to have some enhanced engineering properties? For example, wider access for remohaling or wider space for huge divertors. So then, in a complex process of optimization, using several code, and the school code is a German code, the castle code is a German code. I obtained one area where two planar coils are installed, so if you move this planar coil, you have wide access for remote handling or for to install diagnostics, and also to install large diverters in the case of a reactor. There are some concepts similar to this, but there is no any one build. The property of USD2, as I said, is a 3-period stellarator of 10 liters plasma volume, 260 millimeters major radius, 37 millimeters minor radius, aspect ratio 7. For a stellarator is a middle compartment. Magnetic field axis, in principle 0.1 and 0.05, that could be higher. This is for resonance for common magnetrons. The rotational transport at the center, here and here, 0.74, and at the edge here and here, 0.79, to avoid large low resonance in the plasma, so we avoid large islands. And the magnetic well is positive, but small, but enough for stability and loading. Engineering concepts and design. The most important thing in magnetic confinement are the coils. The coils in this case are modular coils. There are 90 coils. Of these, 84 are modular twisted coils, complex coils, and 6 coils are planar coils. The winding part is very small, 4 millimeters and 12 millimeters depth. And the compactor type is one commercial conductor I have here, I will pass to you. And only 3 layers of 1 counter layer is used. In order to start the definitive design, it is necessary to perform some tests in order to avoid big problems. So, at the beginning, the whole concept was developed. In this concept, you have an external surface and an internal surface, and bars and beams inside different forms, and also the grooves for the coils. The internal part of this 3D printing piece is filled with a filler. The filler can be resin, could be hard plaster, can be low melting point alloys. The result is was good. The piece is robust, is accurate. But the thing I have here, the piece, you can pass very fast. Okay. This is the model, so you can observe and touch this nylon pieces made by 3D printing. This piece and this has the problem that the nylon, the cost of the nylon is 1 to €2 per cubic centimeter. That is a lot because this costs, for example, €200 only to produce this volume. So I try to reduce the cost by reducing the material used. So the truss concept was started. In this concept, you have only bars. You have grooves for the coil defined by 4 three-dimensional curves, and also the volume is filled by a filler. In this case, it's hard plastic. This piece is 320 millimeters tall, but the result was only regular because the piece is cheap. But the piece was a bit warped due to the thermal process of fabrication with lasers, and it took a long time to manufacture to fill the plastic in the volume, to wrap the volume with a plastic. So at the end, a mix of the hull and the truss concept was used in this definitive design. Here you can observe only 3 coils, 1, 2, and 3, but this has 14 twisted coils that are modular coils. Observe the bars that reinforce the structure, the external surface, and also here the internal surface. Though here in this piece you cannot there is no internal surface, so you cannot share the structure. I have here also the piece. I do remember that this is filled with resin with hard plaster, so it is very hard, even as hard as aluminum. And the definitive is larger, but I couldn't transfer this in the plane. An important thing in this design is also that the grooves compress the conductor. So when you wind in this twisted grooves, you wind the coil, it avoids unwinding. So the winding is very simple. For example, in comparison with NCSX, they have a lot of problems. It took a long time to wind these coils. Here you observe that the piece is split in two parts, so you can introduce the vacuum vessel inside, and later you connect the two parts with bolts, and you obtain the full piece. Here you can observe that only one coil has been wind, only as a matter of test, because later you have to introduce the vacuum vessel, and you have to wind the coils later. The cost of this piece, here you see, is 700 euros. It's I think, the cheapest company in the world. In particular, this piece has been filled with acrylic resin. It is not so hard as epoxy resin, it has some advantages also. Experimental validation by construction of USD2. One method to see if 3D printing is appropriate to build stellarators or to build other fusion machine is to build one stellarator to test the procedures. Since the stellarator is not finished, some aspects have been validated, it may be feasible. In this case, measuring the difference between the design, the dimension at the design and the real dimensions, the error observed are 0.3%. But this is a bit high for stellarators. But if you use the same printer and you put the piece at the same point and you use the same material, the difference between the 6 half videos that compose the stellarator, maybe we'll check with the work, will be lower than 0.1%. And this is satisfactory for stellarators. So I conclude preliminarily, I conclude that 3D printing may be satisfactory for the construction of stellarators. Another matter was checked is the fill of the piece with resins or other materials. Many products have been tested. You can see here some samples. Epoxy resin, acrylic resins, polyurethane with fiber, with fiber, each one with one advantage or another. In one period has been filled with acrylic resin. The result is that the filling was fast, only 1 or 2 hours was enough to do all the processes. Another important matter is the winding of the conductor in the groove. In the test performed into grooves, the result was okay because the pressure is not very high in order to be able to wind very fast and enough to keep the conductor in the groove. Only 30 minutes took the winding of one coil, so it's a low value. And another important thing is the crossover that they generate when the conductor goes inside the coil and goes outside, change from one term to another. You are producing magnetic errors. We must minimize this. And the concept is a new concept, cutting the conductor in two parts and passing the cable inside. But the result was satisfactory. The vacuum vessel is still unclear because the cost of the 3D printing materials for metals, for example copper, for example aluminium, and other, is very expensive, and there are not large 3D printing printers for these materials. So a combination of 3D printing to generate some molds and conventional techniques like soldering, laser cutting will be used, I think, at the end. In this case, you see that the stellarator vacuum vessel can be composed by unfoldable surfaces. The surfaces are laser cut and later on among them you can solder and compose the vacuum vessel. It's a slow process, but until the 3D printing of metal to be cheaper, perhaps it's the only solution. But it's ongoing. Its work is ongoing. Now I'm going to show some photographs in order you see the present status and to comment some elements that are important. This is a view of one period. It's composed by two half periods from here to here and to here to here. It's another half period. The legs are definitive legs. In this top view, you can observe again the whole period, and it's important, it seems not important the center, but this is the positioning elements. After thinking a lot, this simple method is composed of a circle here, another circle here, that are in contact with some points that are 3D printed. So you move the piece on the base towards them until contact. Then you have only one degree of freedom, that is rotation. And when all the periods will be there, the assembly will be simple. At least I think it will be simple. 5 minutes? Okay. This is only to see the helical, the excursion of the helical axis, the internal grooves that are very compressed of this area, and also it changes these legs from the side to side. This is the place for the parallel large planar coils. Future work. The test, the initial test, the decision of the device to build, the conceptual design, the detailed design has been finished, and the construction is at 20%. The final validation by electron beam mapping has not been started because the stellarator was finished. And in the next future, try to raise more funds and finish the construction. The long-term aims to try to build a device named Electron with huge copper coils, 3D printed in principle, and at the end we try to fund a device that is a long-term aim, a kind of ignitron similar to the concepts of igniter and alphator and compact test facilities that are spherical total mass. This is a graph relation the cost, the device, and the triple probe. Stellators are on this line, the star is higher is there, ITER we don't know, we'll see. Summary and conclusions. The potential of 3D printing methods to build small or middle-sized stellators is being studied. A stellarator US2 is being built to test the methodology, accuracy, and possible usage of these 3D printing machines. Three concepts have been combined: 3D printing, trash-like structures, and in situ modeling and filling. They are combined to reduce as much as possible the fabrication cost, keeping accuracy. If the result is satisfactory, more laboratories or universities might build these middle-sized, small-sized accelerators for plasma research. And if all questions, interest on any 3D printed fusion device, thank you very much for your attention.
Questions?
Have you tested these 3D forms at liquid nitrogen temperatures? Are they robust when cooled, or do they shatter?
Can you repeat, please?
Liquid nitrogen temperatures, do these structures survive being cooled? So we could consider using high TC coils instead of copper.
I haven't checked this, but I will see if it's possible to understand. This is an idea, really. But it would be a good idea.
Well, I have myself a small question. I have seen from your coils, all the fitting of the coils, they just in and out of a dipole, you know, from stellarator you need at least a quadrupole type of feeding to decrease errors. How are you going to do that?
Yes, here in here, this is the crossover. In this case, the method to decrease, because it's impossible to reduce, because at the end you have a dipole, is to split the coil into parts, one part and another part, and pass the coil inside of the conductor split. So you are reducing, but you are reducing at a dipole. And obviously there is no other better solution in the sense that the error is there. It's a solution.
So I don't see any other questions, so let's thank the speaker again and move to the next.